All right, we all want to be on time and get to the wharf, so I will run right through this. 68 slides, we'll see how far we get. This is my basic information, kind of an amazing run that we've had working on JRuby. So I've been a JRuby developer for 20 years now, which is shocking to me, but also full-time since 2006. In a couple years, it'll have been 20 years working full-time on JRuby and fully half of my career doing this project. So I hope it's useful to some people. I work at Red Hat, which is part of IBM now, so shout out to Red Hat for sponsoring us for the last 12 years. It's me and another developer, Tom Annabo, that are paid full-time specifically to work on JRuby and help out with other JVM language concerns. So we've been really lucky to have a series of sponsors over these years that keep us going. So let's get into JRuby. How many folks have ever tried JRuby for something? All right, how many have put something into production with JRuby? All right, a lot of the same hands, but still opportunities out here for a lot of you others. So JRuby is, of course, Ruby on top of the Java virtual machine, on top of the JVM. We like to say it's a Ruby implementation first. Over the years, people have been afraid of anything attached to Java or attached to the JVM. We work very hard to make the experience of JRuby feel just like regular Ruby. You've got a standard Ruby installation. We use the standard gem commands, rake commands. All the things you do normally with regular Ruby should just run exactly the same on JRuby. We are also a JVM language, though, so we get advantages from that ecosystem that I'll talk about later. Generally, we expect that anything pure Ruby should just work. We've done a lot of work trying to make sure compatibility is solid, make sure that the experience of using JRuby matches regular Ruby and all of the same tools are going to be functional for you. Minor differences like different extension API. The C extensions don't run directly on JRuby and would have to be ported to Java or just use a Ruby or Java equivalent library. We don't support forking because we can do parallel threads. So we can get all of our concurrency without multiple processes and keep it inside one JVM, which can be more efficient in a lot of ways. Thousands of production users over the years, and again, 17 years or more of real-world use since the first JRuby production application was deployed. So we often look at this problem trying to define what is important for a Ruby implementation. So the usability is the first thing. That's where I say we're a Ruby language first. We're a Ruby implementation first. So we work very hard to make sure compatibility is good, the command lines all work the way you expect them, continuing to try and improve startup and warm-up time, but those are ongoing challenges. There's runtime things that are necessary. Ruby has traditionally had trouble with garbage collection, has not had a JIT until recently, and that's still ongoing work. A lot of that we get for free out of the JVM. We can deploy on many different platforms. We have mobile applications in JRuby. We've got lots of server applications. People have built desktop apps. Being able to deploy easily in different environments. Performance is, of course, a usual concern for Ruby applications. And that doesn't mean just straight line execution, getting one task done. That's scaling across many instances, using all of the CPU cores in the system, being efficient about memory use. We also want it to be approachable, so we are always standing by to help people get involved with JRuby and contribute. If you have any issues while running JRuby, just assume it's our fault and we'll help you sort it out. Maybe it's something that you can do better, or maybe it's something that we can fix. And different applications really need different things. So we have tried to take a holistic approach with JRuby to provide the best possible version of Ruby that runs on top of the JVM. So getting started with JRuby is pretty easy. All of the Ruby installers will have support for JRuby. So Ruby install JRuby, RVM install JRuby will pick it up. All works just fine. Only real requirement is that you have a JVM or a JDK on your system, which is available for pretty much every platform, and most Linux distributions have standard packages for that. You also can go to our website and download a Windows installer or just download the tarball and unpack it. There's really nothing to build because it's written in Java JVM bytecode. So you unpack it, you put the bin directory in your path, and JRuby will work from then on, as long as you got a JVM handy. And then you try it out. So here we switch to JRuby, we start up IRB, we can access the Java class Java-lang runtime, we can get the available processors, free memory. So we're using Ruby now in an interactive console to call into the Java libraries. And this works with the entire array of JVM and Java libraries that are out there. If there's something cool in the JVM land, or if you want to integrate with Scala or Kotlin or Clojure code, you can just call it directly from Ruby in JRuby. So compatibility level, JRuby 9.4 is the current major release that we're supporting now. That's compatible with Ruby 3.1, so it's a little bit behind. Something like 98, 99% of the language specs are passing. There's minor little things that you're never going to notice that maybe we'll get around to fixing, but they've not been reported as issues. But everything that you're going to do in Ruby is basically going to work just fine. We also have an older version, JRuby 9.3, so if you've got legacy applications that depend on Ruby 2.6, you could try running them on JRuby 9.3 and still get some of the scaling and benefits of the platform. We always focus on compatibility first, so sometimes the fun work of doing performance and an optimization gets pushed to the side until we can really say that we're compatible with a particular release of Ruby, and then we come back around to performance. So if you run into anything that's not fast, let us know. A little bit about how the JRuby architecture is structured. So of course we are a JVM language, and we defer a lot of the hard problems of implementing a language runtime to the JVM. I don't want to have to write all of the internal native threading and internal consistency of the VM. We let the JVM take care of native threads, and then we get solid parallelism, solid native threading across all of the Ruby applications that you run. I don't want to write a garbage collector. That's like black magic to me. So on the JVM, we've got many different world-class garbage collectors for small, fast heaps, for enormous multi-terabyte heaps, anything that you can imagine to scale in a garbage collector, and we've got an option for it on the JVM. And then, of course, I write a JIT of sorts that turns Ruby code into JVM bytecode, but I don't want to do the hard work of trying to then compile that down to native code across all the different CPUs we want to support. We get that out of the JVM as well. So world-class, just-in-time compilers that take your Ruby code and turn it into fast native code. And ideally, it will run much faster than running the interpreter or even the CRuby JIT. So JRuby really is kind of like a little VM built on top of a big VM. And we try to push as much of the hard stuff down to the JVM so that I can just yell at them to fix things rather than having to figure out how to fix it myself. The compiler pipeline, how we get code into the JVM. We start out with our Ruby code on the one side here. That goes through our parser, which is currently a pure Java port of the CRuby parser, but soon will be the new Prism parser that all Ruby implementations can share. That then could run through our compiler, turns it into intermediate representation, our instructions, basically our bytecodes for JRuby. And then we have an interpreter for those. So we interpret the Ruby intermediate representation, the Ruby instructions for a while. Once we have called a method enough times, we feel like it's important to optimize it, then I will run my JIT code that turns that Ruby bytecode into JVM bytecode. And then the JVM kind of takes over and does the same thing over again. The JVM will interpret the bytecode for a while, profile the types, profile the paths through the code, optimize it, and then re-optimize it. And you'll see this as you run JRuby code. The performance will slowly ramp up and get much faster as time goes on. So of course, we're using the JVM's JIT. We're just referring that hard problem to the JVM. The hotspot JIT, the standard JIT in OpenJDK, is the most widely deployed. It's been around for at least 20 years, 20 to 25 years now. Many different levels of optimizations, very stable, and we've worked very closely with the JDK folks to make sure it takes our Ruby bytecode and optimizes it well into native code. We are also looking at other JIT compilers that are out there. The Graal JIT is a newer, more aggressive JIT compiler that can be plugged into OpenJDK. I'll show some numbers on that a little later. And then there are other JVM implementations out there. IBM also has its own implementation of the JVM called OpenJ9, and that has its own JIT and its own features like saving compiled code to disk between runs, pre-optimizing code, and things along those lines. So all of this stuff can be used from JRuby because we're just the JVM language and we fit into that world. So looking at JRuby on Java 8 through 17, one of the cool things we get about not having to write our own JIT is that as the JVM improves, JRuby improves. There's a saying in the Java world that if your application is too slow, just upgrade to the next Java. And it's usually true, because they're always finding ways to make it optimize code better. So here we look at a Mandelbrot generator script benchmark. And this is the progression over time of how much faster it's gotten just using different newer versions of the JVM. So from Java 8 up to 17, nearly a 2x improvement with us doing nothing at all, just switching to a newer version of the JVM. This is a red-black tree benchmark. A little bit less of an improvement over time because it's really just making a bunch of objects and walking them in memory. But even here, we see steady improvement over time just by upgrading to newer versions of the JVM. And incidentally, these numbers, the Mandelbrot performance here is about 3.2 times faster than JRuby with its JIT, the new JIT that they're working on. And this one is almost 2 times faster than JRuby's JIT. We're always trying to push that level up higher, but generally, pure Ruby code should be faster on JRuby than on regular JRuby. Now, I mentioned the Graal JIT. The Graal JIT is much more aggressive about certain optimizations, and so there are cases where it can do even better to optimize Ruby code. So let's take the Mandelbrot generator, which is largely doing a lot of numeric operations. We create a lot of float objects in the process of that, and so it's cranking through all these objects. One of the things that the Graal JIT can do is actually see that those float object wrappers are not necessary and just get rid of those, use the actual native float, the native double value, and we don't have all the allocation and garbage collection overhead. So for benchmarks like this that are heavy on numerics or a lot of small objects, the Graal JIT can do huge amounts of optimization for us. But the reason we don't recommend that this be used all the time is there are cases where it doesn't help as much. It gets a little too aggressive. It over-optimizes one thing and leaves other optimizations on the table. So it's kind of like you got to mix and match, try your code, and see which versions of the JVM and JIT might work best for you. So garbage collection, I mentioned, of course. I don't want to write a garbage collector, so we use all of the different JVM GCs to allow different size heaps, different sort of metrics for how long of a delay you want, avoiding delays or pauses as much as possible. Many different options that ship as part of standard OpenJDK. And one of the other cool things on the JVM is that there's a lot of tooling built around all of these features. So this is a tool called Visual VM, and this is using the Visual GC plugin. And what you're seeing here is actually a live view of a Rails application being benchmarked on JRuby. You see the heaps fill up, the objects get garbage collected, and you should get a nice steady sawtooth of all of the objects in memory as they get allocated and cleaned up. If you were to see that line steadily go up and not get collected, well, now we know we've got a leak in JRuby, the garbage collector can't keep up with it, we got something we need to fix. But these are tools that just come with JRuby out of the box. So the core and the standard library of JRuby, core classes like string and array are like JRuby, pretty much implemented in our native language, so mostly written in Java. Bits and pieces of those are moving to Ruby over time, so you can contribute to JRuby core just by writing Ruby code if you want. The standard library we largely share with JRuby. So almost all of the pure Ruby gems, we use the exact same versions that regular Ruby does. For libraries that have extensions, we usually have a JRuby version. We've been working with folks like Hiroshi and the other maintainers of gems to get those JRuby extensions into the library, so we're still using the same actual gem, but it has a JRuby version of the extension. So many thanks to all the folks maintaining standard library gems for working with us on that. A little more visually kind of to how JRuby's code base is structured. The Ruby parser I mentioned is currently pure Java, but we'll be moving toward a native parser called Prism. That's a parser we can share with CRuby, with TruffleRuby, with all the other implementations, so we're not constantly reporting the parser all the time. The internals of JRuby, unsurprisingly, the compiler and the IR and our interpreter are all written in Java. Core classes, there's kind of a mix, a lot of Java, but bits and pieces that are in Ruby, bits and pieces that are in C. And then the standard library, again, a mix. A lot of Ruby code, a lot of pure Ruby that we share with regular CRuby, but some of our own JRuby extensions too. It's good to contrast this with the way it's structured in CRuby. A little bit more heavy on the native code side. They also are going to start moving toward the parser, the Prism parser, and they have a Ruby parser generator that they're using. So that's why I've colored the parser a little red here on this one. The compiler in IR, the base part of the VM is written all in C, but the new JIT they're writing in Rust. So it's still native code, but a new language to throw in there. Core classes, pretty much solidly in C. And then again, the standard library, similar to us, mostly Ruby with some C and extension libraries there. So I mentioned the visual VM profiling and monitoring tool that you can use with JRuby. There's another one that's also called the JDK Flight Recorder. Now, this is a way that you can do low-cost monitoring and profiling of even production applications. With only a couple % hit to your throughput on an application, you can monitor for performance problems and see if there are particular methods or particular objects that are taking up too many resources. This is just a quick view of that. Here we're running a memory profile on an application in JRuby, and you can see things like Ruby string, Ruby array. You can see blocks, which represent Ruby closures, Ruby blocks. And we can see how many gigabytes are being allocated to all of these different things. By monitoring this over time, you can hunt down in your code where you're creating too many strings or too many arrays or other objects. And there's a whole other set of tools in Mission Control and Flight Recorder. So I mentioned there's a lot of ways to contribute to JRuby. Of course, any of the JVM languages are fair game. If you want to write a library, a plugin for JRuby in Scala or Kotlin, it should work just fine. You can call those libraries from Ruby code. You can integrate it into JRuby. We try to keep the code base pretty straightforward. So if there's a core class, you put Ruby at the beginning of it. That's our version of it in the JVM Java world. Ruby string, Ruby array, Ruby hash, and so on. We have many levels of complexity. So you can come in and you work on a simple thing like array each and just iterating over an array and see if there's features that need to be fixed or added there. All the way up to, if you have ever done compiler 101 stuff at university, you can come in and help us work on compiler optimizations at that level. And there's a lot of non-coding tasks that we can always use help with. Run tests on your favorite library, report things that don't work, try out your own applications and let us know what's missing or what we need to fix. We really need the interaction from the community to keep JRuby moving forward. All right, so I mentioned one of the other key areas that's important for Ruby is performance and scaling applications. So scaling has been a classic problem on CRuby. Since we don't have real parallelism with the threads in Ruby, we need to run worker processes. And no matter what you do, even with copy on write tricks and pre-forking and all these other tricks, you're still going to end up duplicating some amount of resources. At a minimum, each one of those processes is going to have its own garbage collector, doing its own thing, interacting with memory in its own way. And that's not the most efficient way to do garbage collection. Much more efficient to have a single large process with a good garbage collector that can manage the whole thing. JRuby, we believe, is an excellent solution, perhaps the best solution for scaling Ruby out horizontally. It's a single multi-threaded process that can run your entire site. So rather than having 100 workers to be able to handle 100 concurrent users, you just need to turn that knob up in Puma, say you want 100 concurrent requests at a time, you'll get 100 threads, one process, handling the entire application. So as an example, a little baseline Rails application. So this is running on Postgres on an IBM virtual PC instance equivalent to about 8 CPUs and 32 gig of memory. This is a little bit older. I ran it with JRuby 3.2. Numbers have not changed significantly for 3.3. So 16 workers on regular Ruby and 16 threads on JRuby. And then we just hit it as hard as we can. So this is just the blog post app. How quickly can we bring up one view of one post? So if we look at the performance, I mentioned that there is a startup and warm-up thing that we're trying to improve with JRuby, and they're trying to improve this in the Java world as well. You'll see that JRuby takes a little while to get going. That's the warm-up curve. That's us profiling code, eventually optimizing it, eventually turning it into JVM bytecode, and the JVM taking it from there and eventually optimizing it to native code. But we do come out on top, even ahead of the JIT project that they've now integrated into JRuby. So looking at this more directly, here's JRuby with 1,700 requests per second, JRuby with JIT 1,500. So it's not bad. We're not getting a huge gain going on JRuby, but we are consistently faster here. Now where it gets interesting is how much memory we need to accomplish this. So I was cranking through this with 50 concurrent users or something. If I don't tune JRuby at all and just let the JVM eat as much memory as it wants, it ended up using about 3.4 gigabytes of memory, which is a lot. It doesn't need that much, but the JVM is designed in such a way that if it sees a lot of memory on the system, it's going to grab it and use all that memory as much as it can. You can change that and tweak it so it doesn't use as much. So I've got a version here that I'm going to run with 300 megabytes instead, which ends up being a little under a gigabyte total memory in the native memory. And then using the G1 collector, which is a more memory efficient version of the GC, that ends up at about 1.6 gigabytes without any tuning. So then on the JRuby side, of course, we need a process for each one of these. 16 times a 100 meg Ruby process, well, that's 1.6 gigabytes right there. We throw the JIT logic in there, and I know they've improved this, but the JIT process, or JIT logic, also takes up extra memory. Now we're looking at about 2 gigabytes to have the equivalent concurrency on regular JRuby. So we go back to our requests per second. We're good. We're a little bit faster, even with the forcing the heap down much smaller, still faster than JRuby with JIT. But if we look at this in terms of RPS, requests per second, per megabyte of memory, then JRuby really starts to come out on top. So this is just with 16-way concurrency, and already JRuby way out front. Anybody who's doing cloud deployment knows what you're really paying for is the memory that you're renting space. Because you can't share that. You can share CPU resources, you can share some of the network resources, but memory you have to have in your instance. Can't be shared easily. That's where the cost goes. And if you can reduce how much memory your application needs, that's where you're going to save money. Let's take this up to 180-way concurrency. Now it's clear where the advantage is of having a single process with many parallel threads. We can take this up to 100, 1,000 concurrent users with only a small increase in the total memory used by the application. With JRuby, each time you add one of those concurrent users, it's going to be another process and another wasted chunk of memory. So this is where it really translates to real money in a deployment scenario. So let's talk about something a little bit more fun. One of the other great areas of the JVM is all of the support for cross-platform graphics and GUI libraries. So on the graphical interface side, we have Swing, which is built into the JDK. This is the classic Java GUI toolkit, easily callable and scriptable from JRuby. It's very clean, it's very cross-platform, and very simple to build quick and simple user interfaces. You write that in Ruby, you send that to somebody else, they can deploy it on JRuby, no native libraries required, you've got a graphic interface on your application. Another toolkit, the scalable windowing toolkit, which is what the Eclipse platform uses as its user interface. This actually plugs into the native widgets on the system. So it still has a little bit of a native component, similar to some of the GUI toolkits for JRuby, but when you download it and install it, or install it through one of the gems that wraps it, you don't have anything that you need to build, and it will just work out of the box. There's also a newer one called Java FX. We have a JRuby FX wrapper around that, and this is more of a Flash kind of scene-based vector drawing. You draw more of your widgets. It's a little bit more like doing a user interface on a web page than using buttons and fields. So from here, a lot of Ruby libraries have wrapped these options and turned them into Ruby libraries that are nice to use. So the version 4 of the shoes library, which is intended to be a quick and easy way for people to play around with graphical interfaces in Ruby, actually is built on top of JRuby. And so you write code like this, it's going to use swing under the covers, present your graphical interface using JRuby, and there's nothing else that has to be installed. It's just a pure Ruby application on JRuby on the JVM. Another one I'm very excited about is called Glimmer. So Glimmer is a DSL for building graphical interfaces, very heavily being developed right now, multiple backends and multiple toolkits, but the version that runs with JRuby and the standard windowing toolkit, SWT, is probably the most mature. You can build full-size desktop applications with a very nice DSL, and then you'll know that that DSL can translate to other platforms and potentially even back into CRuby if you want to go that direction. I mentioned JRuby FX. There's a little snippet of how JRuby FX DSL works, building up components using layouts and rectangles, and then scripting a timeline for an animation. I haven't done a whole lot of work with this, but if you're interested in that kind of development, we have JRuby FX as well to wrap that. And then there's even fun things, like there's a plugin system for Minecraft that is written for JRuby so that you can write plugins in Ruby code and they will deploy and run. You build up your interface with the standard Android GUI builder, but then you script all of the logic and all of the events behind the scenes using to do all the database access. So it's integrating both sides of that world, and it really is a Ruby application running on Android. We have a Rubato IRB demo application out there. We used to have this deployed in the store, but it turns out when your application says that it needs all the system permissions, they don't like that. So that got pulled from the store, but the APKs are out there. If you find Rubato Core, which is JRuby itself, and Rubato IRB, which is the IRB interface, you can get all of this and play around with Ruby on your Android device. So we are working on updating this. We're working on pulling JRuby 9.4 in there, getting the version of Ruby updated. We have a branch that's working well now. We've done some demos with this in the past year, hoping to get back to this and get a full release of Rubato out that supports current JRuby and all the current Android features. All right. So last big section here, we're going to talk about some of the new, really cool JVM features that really make JRuby have a compelling story going into the future. And the first one is fibers. So we just saw an excellent talk from Vishwa and Ishani on concurrency and fibers. I recommend you go back if you want to learn more about fibers. It was a really nice treatment of the whole topic. But we're talking about basically little micro threads, explicitly rescheduled. They stay on the same thread. The CPU doesn't have to context switch. The operating system doesn't have to get involved. And we can hand it off to another line of execution and go back and forth, and potentially do that hundreds of times in a given thread without ever leaving the CPU behind. Looking at this graphically to kind of understand how fibers and threads work the way that they see more visually what's happening here. So here we have our execution flow for a little HTTP server, okay? We've got our first thread over here. This is just going to do a normal threaded request handling. We accept a socket. Now we have to wait for I/O. We're waiting for a request to come in. At that point, the thread gets descheduled. We're blocking on I/O. We can't make any progress. We're wasting time on the CPU. The CPU dumps us off, goes and runs some other code, and then maybe will come back to us at some point. So it comes back. All right, great. Now we've got our request. We handle the request. We've got a response that we need to send. What happens now? Again, we're waiting. We're waiting to make sure that the request or that the response was received, that we don't have any more work to do, and we get descheduled. We're wasting time and wasting resources again. Now, what we would like to do is be able to take advantage of that time, that blocking time while we're waiting for a request. So on this side, we're going to use fibers. So we got fiber number 1 comes in here, same thing, accept the socket, waiting on I/O, but at this point, we say, okay, well, we can jump over to another fiber. Let's handle another request over here on the same thread without losing the CPU, without wasting time with a context switch. Now we've got fiber 2, accept a socket, wait for that request to come in. Okay, now we've got our request on fiber 1. We jump back. We can handle that request, we can send the response, and so on. So we make better use of the native thread and of the CPU that we've scheduled during that time by having fibers explicitly hand off control to each other. So fibers on JRuby have traditionally been a little bit of a challenge. There was no way to do native fibers and do that sort of explicit handoff in a given thread, so we just had to simulate it with threads. And threads are very resource intensive. Most operating systems aren't going to let you spin up more than a couple thousand at a time. They have to context switch at an operating system and CPU level, so the handoff is much slower. Just really wasn't scaling very well. And that's exacerbated by the fact that Ruby world is kind of moving toward thousands and tens of thousands of fibers using tools like async, using the server Falcon. We need to have a better solution here. So let's do a little example here. Let's try and create 100,000 fibers, which might be possible. It definitely could happen in Falcon if you're running with high concurrency and lots of requests coming in. We try to run this on JRuby, well, it doesn't work. Like, we blow up. The JVM just gives up on us. There's too many threads. It can't allocate new ones, and there's nowhere to go from there. If you can't allocate a thread, it's going to raise an error. In this case, we actually end up seg-faulting the JVM. JRuby's really good at seg-faulting the JVM. We found lots of bugs. So we blow it up. It's not going to work. And like I say, this is going to happen anywhere past 2,000, 3,000 fibers, which is not going to handle the way people want to do things these days. So this is all bad. But we've been complaining endlessly for years about this. We told the JVM folks they're going to need to add fibers. They're going to need to add virtual threads or threadlets to the system. Now we have Project Loom. So Project Loom is an OpenJDK project that adds real native fiber support to the JVM. So all we have to do is plug into virtual threads, which is what they call fibers, basically. And now we can actually start to run with tens of thousands, hundreds of thousands of fibers. So I was real excited when they finally got a build of this out that was ready to be tried. They wanted people to come in and start experimenting with it. So here's my commit a few years ago, enabling virtual threads, enabling Loom fibers on JRuby. It took a lot of work. That was about it right there. So rather than tossing fibers into our thread pool that we'd been maintaining, because we had to use native threads, I just asked the JVM to give me a new virtual thread for every fiber. And that was the only change that I had to make. So how does our benchmark work now? It actually runs really well. This is competitive performance to CRuby's optimized native fibers that it has. This was actually on an early build of Loom, so I expect that these numbers have improved. But just the fact that it's working is amazing, and all I had to do was one line of code change. So 100,000 connections concurrently on JRuby? Yeah, this is actually a possibility now. Aquatics is the fella that works on Falcon and async. He's done some demonstrations of Ruby doing 1 million concurrent requests on that framework. Now with actual native fibers, we'll be able to follow along with that in JRuby. So this is awesome. Like, I didn't have to do anything. I just had to wait until the JVM guys did it. So similarly, native libraries have been a challenge for JRuby. So Ruby kind of grew up with C. Native libraries go hand in hand with Ruby. Ruby really has been kind of a DSL for POSIX. It's really built around a lot of the same concepts. If you look at I/O, it's mapped to a lot of the same functions in I/O for POSIX. C extensions are used to integrate new features into the runtime itself. More and more of these are moving to FFI, which is programmatically calling out to C libraries rather than writing C code to do it. But that process has been slow. We need to support as much of this as possible so people can take their applications and bring them over to JRuby without a lot of problems. Extensions are tricky for us. Usually, if it's written as a C extension on JRuby, it will have to be ported to Java or some other JVM language. Potentially, you can use a pure Ruby version, and it will run just as well, because we do optimize pretty well. But we do recommend using something like FFI or Fiddle, which doesn't require anyone to write C code or Java code. You just call out to the library from Ruby. So that's where our recommendation is. When you use something like FFI, what we actually have is a structure like this. So you've got your user code at the top that wants to call some native library at the bottom. We go through our little native runtime called the Java native runtime. That creates a little stub code that calls through Java native interface. So we got a Java side of that, and then a C side of Java native interface. That calls into libffi, and then finally we get to the target library. So you haven't had to write any C code, but there's a lot of layers here. Too many different transitions that we have to go through. Into the JNR runtime, into JNI, then finally out to native, asking FFI to do stuff for us. The performance isn't as good as we'd like. We need improvements here too. So this is where another JVM project comes in called Project Panama, which brings native optimized FFI to the JDK. So this is a new foreign function interface for the JVM. But the JVM knows about this and can optimize these calls. It can get rid of most of those layers and make those native calls much more quickly. It also has a built-in API for accessing foreign memory. So if you need to allocate stuff on the native heap and work with memory directly rather than going through the garbage collector, it can optimize that and make it much faster and manage that memory for you. It also includes a really cool tool that you can point at a C or C++ header file, generate a stub in Java code, and then you can call that even from Ruby. So it makes it much quicker to pull a library in, get all of its functions and structures bound, and then use them directly. So this is what it looks like if we're using Panama. We're just starting to integrate this into JRuby now, but your user code would call into some generated code by Panama. Panama works with the JVM to do that native call as fast as possible, and now we've cut most of those layers out, and it'll be significantly faster and much better management of resources on the native side. There's two projects that are using this now. The SQLite support on JRuby is actually provided through the standard SQLite native library. Currently, that is a JNI, Java Native Interface plugin. But the Java Native Interface isn't very efficient. So they've started playing with Panama to integrate SQLite into the JVM. Early results are looking about twice as fast. So that will translate into better performance for JRuby users on SQLite as well. And of course, I mentioned the Prism parser, which is a C library. Right now, we're just integrating that with our FFI layer, but very soon we'll be able to hook that up with Project Panama, call directly out to the parser, get our Ruby AST back very quickly, and everything will run a lot faster as a result. So this is making native integration much faster for us. All right, so talking about future of JRuby here. So JRuby 9.4, I said, is the current stable version, Ruby 3.1 compatible, runs Rails 7, 7.1, just great. It's moving more and more towards a maintenance mode. It's kind of done on compatibility, starting to work on a little bit of performance here and there, but that's the best place for you to start if you want to experiment with JRuby today. We are really excited for these features and other JVM features that are coming up. So we know that there's a lot more that we can use on the JVM. We're continuing to work with OpenJDK folks. And for the first time, I can make a big announcement. We're going to JRuby 10 for the next release. Very excited about this big leap forward that we're going to make. So JRuby 10, we were really excited about calling it JRuby X, but for reasons I won't go into, that has kind of become a toxic brand, so we'll just go with JRuby 10. So this is our big leap forward. We will have Ruby 3.4 compatibility. That's not even released yet on JRuby side, but we're going to have JRuby 10 release around the same time as Ruby 3.4 this year. Moving up to a minimum of Java 17 or possibly 21. The motivation for 21 is that that's where native fibers come into the JVM. So if we could depend on that always being there, obviously we can do a lot of cool things with fibers that we don't have to worry about. It will be using the Prism parser. We'll probably still have our standard Java parser for when we don't have the native library available, but moving towards using the native Prism parser. Already I've started to do a lot of really cool optimizations. I'm excited for what we can do with this. Being able to move up to a higher version of Java gives us access to a lot of optimizations and APIs that we didn't have before. So this is definitely our biggest jump, and we're looking for people to contribute right now. So what can you do to help? Whoops. So help build JRuby 10. So we are jumping from Ruby 3.1 all the way to Ruby 3.4, and we need help from users like you to implement those features. That can even be written in Ruby. If there is a new Ruby function that was added to core or string or array that can be written in Ruby, you can submit it that way. It'll probably optimize just fine. If it doesn't at some point, well, we'll find another way to optimize it, or we'll port it into Java. But at least we can get the compatibility and functionality there, and you can help with that. Testing out your libraries, testing out your applications. Even if it's just run bundle install with JRuby on your app, and let us know what native extensions we're missing, or what libraries aren't available. Just let us know what it is that we can do, what gaps we can fill in to make JRuby useful for you. You can help us triage any of our 700 open bugs. I guarantee they're not all valid anymore, but I used to go through every couple of months and review every one of those bugs, and it damn near killed me. So need help going in there, finding these old bugs, testing things out again, and let us know if there's issues that are no longer valid. And we are standing by to work with you. We have a channel on the Matrix chat framework. It's sort of like Slack, but it's open source because that's what we like. So jump into Matrix on our JRuby channel. We'll be happy to show you around, direct you towards some lower level, entry level things that you can do to help work on JRuby. But there's at least a couple of us idling in there all the time. We do all of our development discussions out in the open, so come and join the team. And that's all I got for you today. Thank you very much.